Good afternoon, everybody. Hello, I'm Nate Mosier. I am the department head in agricultural and biological engineering, and it's my great pleasure to welcome all of you to this event here for lunch. I'm very happy to introduce the event as well as introduce our speaker today. The College of Engineering has been doing these events for asking recently promoted associate professors to give a little bit of a reflective talk about their path to here, research and personal and professional, and then some reflection about what comes next. So that's, I think, a very important thing to do is reflect as you cross some very big milestones, and certainly as academics, promotion and granting of tenure is certainly a big milestone. So I'm very happy that the college provides a venue to formalize this, and I think as well it allows opportunities for recently promoted faculty members to make some connections across the college. We're a very large college. As you hear Dean Rahman say, engineering at scale is certainly something Purdue does and tries to do and excel at. So this is a great event to sort of highlight the breadth, diversity, and depth of the research that faculty in the College of Engineering at Purdue do. So with that, I'm very happy to introduce our speaker today, Shomali Chatterjee. She has a long and winding road that brought her here to Purdue and to here with us in agricultural and biological engineering. I'll give you just a very brief sort of background of what she's been working on and how she came to see us. So she has a long connection with Purdue, and some of her graduate work and postdoctoral work was here at Purdue University. Has a background in computer science and applications in computer science. And one of the big first applications was in biomedical engineering and in applications in human health. And when she came back to Purdue, she joined us a decade ago, 2014, as a visiting assistant professor in computer science. And then a few years later moved into a research faculty position in agricultural and biological engineering. And it may seem like a bit of a switch from computer science to agricultural engineering, but we do have a lot of faculty with expertise in biotechnology. And so maybe my short description of what we do in ag and bioengineering is we're the place where technology touches food systems. So you imagine any kind of technology. A century ago, that might be machines and mechanical and mechanization. Mid to late 20th century, it might be biotechnology. Much more recently, it's certainly digital, data science, artificial intelligence, and machine learning, and that's really where Shomali's story comes in. So a lot of the work that she does is focused on applications of machine learning and artificial intelligence. And one way I like to describe it, and using some words from her, is right-sizing machine learning so that it can operate well in smaller devices, lower power devices that may not have the connection to the cloud and the deep computing resources that ChatGPT or other more familiar AI systems might use. And certainly there are wide applications of this in places like agriculture and forestry and places that are not near urban centers or not with the high connectivity to the backbone of the internet to do a lot of data processing. And there's certainly applications, and she'll speak about this, I'm sure, as well, in continuing looking at using these tools to better understand the secrets of biology, not only in human health, but in plants, animals, insects, microbes, and all that as well. So please join me in welcoming Shomali here to the front to give her presentation.
Thank you, Nate. So with that, I'm looking at the clock. So I think I'm the only speaker, so I can take as much time as I want to. Just kidding. But that's how I did not time my presentation. But yeah, roughly 15 minutes. So that's the topic: deadlines, detours, and destinations. So navigating the path from assistant to associate professor. I did my PhD in biomedical engineering at Purdue. Then I went for a postdoc to UT Austin. Came back as a visiting assistant professor in computer science, and then finally I'm an associate professor in AB and EC by courtesy. So what I like to think of is bridging the two domains of biomedical engineering on the one side and computer science. So a lot of my work is user-inspired. So, think of applied machine learning applied to two thrusts, and I'll show you what the two thrusts in my lab are, but that's how the bridge, and I'm very excited to have worked with both sides so that I can look at some of the real applications, some of the real needs on the one hand, and use some of the jazziest, glitziest new tools and come up with algorithms that are made for these applications. So giving you a little bit of a story of my funding trajectory. So the first grant is always a great thing. I just realized the laser pointer doesn't work, so I'll use my finger. That was my first grant when I was transitioning from visiting assistant professors to assistant professor. That was an NIH R01. And show of hands, if you know where that came from, it actually came from NIAID. I'm very good at doing that, show of hands, and then I don't wait for your answer. That's because of the time given to me. But that came from NIAID, and it was in the continued development and maintenance of the MG-RAST metagenomics pipeline. So that was with a bunch of folks in Argonne National Lab, Volker Meyer, and then from Purdue Computer Science, Anant Krama, Purdue ECE, and myself. So that was great because what we did is we were able to come up with a scalable database that could keep up with the increasing demands put on it by the increasing popularity of this MG-RAST metagenomics database. So think of metagenomics, the MG-RAST database as a Google for microbiome. So you can basically put in lots and lots of these microbiome data and get analysis out of it. So the second one, which I think kind of got me to look at some of the ag applications, digital ag applications, is the Lilly Endowment Grant with a whole bunch of folks here at Purdue. It was a $40 million grant. But the important thing that kind of resonated with me is how do you have these databases that can, again, scale to all these different data sets that are coming from all these different noisy sensor data in these heterogeneous connected forms. So that was the vision. And that led on to coming up with energy-constrained cyber-physical systems. My first segue into DoD was this ARL center. It's called A2I2. So here, think of IOBT, Internet of Battlefield Things. So again, kind of similar flavor, but here think of different kinds of sensors that are there in the battlefield. And then finally, I had a lot of fun having, being able to work with private industries such as Adobe Research. I mentioned Adobe Research, but early on, we worked with Microsoft Research, kind of getting in-kind cloud compute resources from them and getting lots of serverless cloud computing papers with them. And then finally, last but not the least, we have my NSF career. This is my second year running. How do you run robust and adaptive streaming algorithms from these various kinds of data? And the jazziest, newest kinds of data that my lab deals with is LiDAR data. So think of LiDAR data. And LiDAR data, what happens is you have a lot of point cloud data. And this point cloud data is very sparse. So how do you use the kinds of, say, for example, denoising autoencoders, et cetera, that can help you encode the data, the signal, from this point cloud data, which is very sparse. So think of this additional kind of data set that is now in my tool chest of different kinds of sensing data. So with that, these are the main funding themes. I'm not going to rattle them out, but I had a lot of fun with starting off to build a large production scale database for metagenomics. This is MG-RAST. So one important lesson that I learned early on is that when I worked with MG-RAST, this was an actual production scale infrastructure that was used extensively by people all around the world. So we could not take it down, right? So we basically had a sandbox site here at Purdue, and could we do some of the different algorithmic maneuvers without basically taking down this production scale infrastructure, but then coming up with the innovations and porting them to the infrastructure so that we don't break it, right? So that was very exciting. And then one of the very resonating and kind of something that I still do is this theme of handling large amounts of noisy data. So this noisy data can be from inexpensive sensors, or it can be from different kinds of genomics data sets. So one of the latest kinds of genomics data sets, for example, my lab is handling, is single-cell genomics data. So again, you have noise from genomics data sets, and you have noise from these ubiquitous sensing sensors. And how do you build resilient and energy-aware CPS? So like Nate mentioned, one of the things that we do is we right-size these algorithms for very small devices. Now, if you think of small devices, these are not really small devices. This is an example of the test bed in my lab. You have this heterogeneous compute fabric of various kinds of mobile GPUs. So these are not these really large H100, A100 GPUs, and these are not small devices, but these are small in contrast to the GPUs that are there in these, big data centers. And these small devices are also running a lot of the self-driving cars, etc. So can you right-size these algorithms to run on these small devices? And not only that, can you do that in a latency-aware manner? So a lot of these algorithms, including the center that we just won, the NSF Chorus Center, is to do with lots of deadline-driven algorithms, right? So deadlines, I think, is a part of my real life and my research life. So in these deadline-driven algorithms, can you run these algorithms on these small GPUs and still be able to give the kinds of guarantee, the kinds of latency timelines that these different applications demand? And the last one, I think I've had a lot of fun. So my students, they go for internships to these tech industries, Adobe Research being one of the latest ones, and students who've graduated and gone on to NVIDIA. So we are writing this latest article, and I'm hoping, in a few months you'll be able to see it with the authors from Google, NVIDIA, Adobe Research, and also academia folks, and also people who've started startups, including myself. So what is the perspective? What is the way to collaborate with industry, and lessons learned? What does academia do well, and what does industry do well, and how do you form an alliance? And this actually came out of the CPS, NSF CPS PI meeting earlier in April that I co-organized. And then we also had NSF Center workshop here at Purdue last December. So we clubbed resources with Shahbaz from computer science, and we are writing this paper together. So I'm very excited about this paper to forge these alliances with industry. Okay, so this talk was actually really hard to make, and I had to really scratch my head and go down the memory lane and see what were some of the first papers that we worked on. I see Milind is here, Saurabh is here, Volker is now in Germany, Kanak is now in Adobe Research, Anant. So I think these were, and Ninghui. We came up with some of the ways in which I could tap my expertise from the past and also think of some of the pressing needs in the domain. So one of the things that we saw, and this was one of our first papers in a supercomputing conference, it's called ICS, and this is about making a domain-specific language for genomics. So I'll try to not make this too technical, very little snippets of technicality here, but what we saw is because you have so much genomics data coming out, the algorithms of the past were quickly kind of getting worn out, and you had to come up with new algorithms. So can you expedite the pipeline of making these new algorithms? So not only have efficient algorithms, but make the pipeline of making and designing new algorithms more efficient. And for that, what we did is we saw what are some of these recurrent algorithmic motifs or kernels that we call kernels that are existing across a vast swath of these genomics algorithms, right? So one example, if you're familiar with the genomics application domain, is you have this thing called similarity computation. And there's this other thing called k-merization. So the output of k-merization goes to similarity computation. So can you make it such that the connection between these recurrent kernels is more seamless? So we came up with a genomics DSL called Sarvavit. It comes from the Sanskrit word all-pervading, to make the ability to create these new algorithms more efficient, so that these genomics application users, they don't have to do these low-level optimizations. They could use Sarvavit and come up with these more efficient algorithms. The second one that we did is federation in genomics pipelines. So federation in genomics is a way to scale computational infrastructure efficiently across multiple different organizations. So can you take the compute resources of these multiple different organizations and be able to use that compute pool to be more efficient in terms of computation? So data repositories and computational resources across these organizations, can you use them more efficiently in a federated infrastructure? And we again tried that out amazingly with MGRAST, because we had this real infrastructure that we could federate using our applications. So both of those were vision papers. And then we quickly wrote up 2 grants. So one was an NSF project that we wrote up. We got 3 very goods, and you can't see it here. Their panel recommendation was highly meritorious. And then we also, later that year, we wrote this NIH project, continued development and maintenance of MGRAST. And this got funded. I broke the news early from NIEID. But the funny thing was, this was declined, which kept me scratching my head, like 3 very goods, highly meritorious, declined. So sometimes things don't make sense, but keep at it. And the next one with a much larger amount, $3.7 million, got funded. So there we were. So that was one of my early tastes of success, which was very exciting. And then I fast forward quickly, right, to 2021. 2021 is like the thick of COVID summer, right? So I really had nothing much to do that summer, especially I remember June and July. I really put my head down and I wrote my career proposal. In some ways, I was very grateful, lack of distractions. I could just sit and work, nothing else. And I actually have proof to show you. I think I kind of went ahead of myself. There was a 67% increase in my citation count. We got a lot of papers that year. So I think my students were also very energized by, just doing work. So I think we were working away. So my career proposal, it came up highly competitive. It is energized by the idea that in 2025, there'll be 31 billion IoT units. There'll be all these sensing units, right? So can you make these dumb sensors more active? And by active, I mean not just sense, but also actuate. So a very important part of cyber physical is it has to sense and then perform. It has to sense and then actuate. So my goal was using some of the latest technologies. I had a few different things that I had in my proposal. One is federated learning, right? So federated learning was really made for this kind of a scenario where you federate learning using these different sensing devices. And if you remember early on, we had used that federated compute infrastructure in a slightly different way when federated learning was not that jazzy in 2017. And then we went on to use the real way these days, the way you federate computing. And so we have federated learning, we have serverless cloud computing, and then we have this on-device computation. So these are the 3 technical tenets of my career proposal. And to give you a little bit of a takeaway on serverless cloud computing, it's almost like on-demand cloud computing. I tell my students for the grad course that I teach, think of it as the Uber, right? You don't have to take the rental car for the whole week. You just take an Uber ride, and you just pay for that A to B destination. So just exactly the amount of compute that you use, that on-demand computing, that's the amount that you use. So again, for this use case, to be able to use that on-demand serverless computing is very helpful. So I tied all of them together, and this was the result. So that date, 4th December 2021, is when I heard from my program manager that is actually looking to fund my career proposal. I jumped. I really want to jump again because I was like, oh my gosh, this is so cool. And then the next mail that I did not put in here because I was cramming stuff in there is like, hey, by the way, can you increase your budget? Because I see that the reviewers pointed out that you didn't budget for broader impact and you didn't budget for your summer salary. So he asked me to increase my budget. I'm like, no problem, I'll do my work. That was amazing. Also, I wanted to actually point this out. We amazingly, remember I told you I'm very deadline driven. I don't know if I paused on that, but there's the deadlines, right? One of the features. So we got a 2-day extension in the NSF deadline, which is unheard of. So what happened is that year, all the career proposals were due on the same day. All the different directorates, the deadline was moved to the same day, and guess what? Their infrastructure collapsed. So the deadline was extended by 2 days, and I reached out to some people, oh my gosh, I got 2 extra days, and this was so amazing. So Mithuna, who's not here today, he gave me some very nice points. I put them in. But he also told me this, which I think is a nice thing to remember when I mentor other people. I highlighted that because I patted my back and I was actually looking up these emails, making this presentation. I was like, oh, I think your proposal will be among the top quarter of proposals easily. So when you mentor people, it's nice to kind of, throw out these little candies. I feel like, oh my gosh, this is good. I already feel good. And then look at the timestamp for Shuman Banerjee's email. It's 11:11 p.m. Can you jump onto a Zoom call? I'm like, oh my gosh, I love this guy. So yeah, we hopped onto a Zoom call and he told me what to do. I just gave him the first few pages. So don't give him the entire proposal when it's 1 day away, right? I gave him the first few pages and I told him, hey, do you have any quick comments? So that was amazing. And then this is celebrate our submissions, right? We have a lot of submissions from our lab. Not all of them get accepted, but as soon as my July submission of my career was done, it was COVID, so we went for a road trip. We went to the Upper Michigan Peninsula and we just spent some time. So celebration. So deadlines. Deadlines rev me up. And this is like a mouthful, so I don't have time for that. Maybe I'll take 2 minutes for this slide. This is a little bit of my trajectory, like in terms of papers. I had to again be like, I had to pick papers very wisely because I was like, okay, pick that, don't pick that. But this was one of the first papers where we got the best paper award. And I really picked this paper for a very specific reason. If you see, there is microRNA targets. So if you know this year, the Nobel Prize, one of the Nobel Prizes is on microRNA. So one of my first pieces was, how do you find the targets of these microRNA in a distributed manner? So there was some parallel computing in it, distributed computation, but it was also driven by the fact that a lot of these regulatory RNA, they have a lot of side effects because of these promiscuous interactions. So can you define the interactions, like find the interactions in a way so that the side effects from these off-targeting is reduced? So that was the ML for One Health. So I grabbed onto, that's something that a professor should learn to do, and I'm doing that. I think One Health is one of Purdue's focuses, and hopefully that qualifies. And of course, we have more work with One Health. And then we continued some work with microRNA, all of this published. Then SOPHIA, I want to stop at SOPHIA a little bit because apparently I learned this from the two Purdue folks, Andrew Umlauf and Matt Halliday. Andrew told me this was a first action allowance, and apparently that's very rare in software. So it's almost like you submit a paper and a reviewer does not ask for any revisions, it just goes through. So SOPHIA was granted, it was my first patent again. So amazing. And so I was very happy that it was a first action allowance. And just a couple days ago, as if in time for this talk, we just got the second one granted. It's called Optimus Cloud. And these two are what led on to KeyBite, which is my first startup. It's a little bit weird saying my first startup, but my one and only startup. I'm the CEO of the startup. Saurabh Batchi, he's the CTO, and it is to do with how do you do this real-time configuration of these cloud-hosted databases so you can give them maximum performance for minimum dollar. So if you want to decrease your cloud computing costs, come to KeyBite, right? So that, and actually, I see Andrew sitting there as well. He's a hard taskmaster. I took the ELA class, and he told us, hey, if you talk all this technicality, you have to tell people exactly what it's going to do. So I think I learned that from Andrew, that one of the things KeyBite is going to do, this is your takeaway, if you want to reduce the cloud computing dollar costs, come to KeyBite. We will give you the maximum bang for your buck. So then I think this is the other thing. I'm very excited about the drone angle. So they tell you in your career proposal, have something that is really in your current research portfolio, then have something slightly out there, and then have something way out there. So the drone thing was a little bit way out there. And that was the most physical in the CPS, cyber physicality. So entrepreneurship, software artifacts, this is something that I'm very gung-ho about. So these days, whenever we write code, we also have these software artifacts. And ACM has this thing that they're going to individually evaluate your software artifacts and see if your results are reproducible. So you submit a separate software artifact submission, and then you say, give 10 points. And then there'll be independent evaluation to see that if they can actually find that your software results in those numbers that you have reported. So that is something that I'm very excited about because I don't want the technology to die in my lab. And the P in CPS, so I think we are working more on that physicality. The P is the physical, so cyber physical systems. So I now have a cyber physical lab where we have, if you remember, those mobile GPUs, and then we also have all kinds of drones. And then the latest, Chenny went to Adobe Research, and he has diffusion models. So at this point, I'm like, you know what? No more new things to my lab. So now I'm going to start putting these in different buckets. So the way we have an ECCV paper this year from diffusion models that Chenny presented in Milan. And now the angle with CPS is, can you use diffusion models to simulate various conditions in CPS? That is going to tie in nicely with the latest center that we won, Chorus. So this is detours, lots of detours. So deadlines, detours, and of course the last thing is destinations. These are the two thrusts of ICANN. I don't have to read them out, but Internet of small things. Think of small things, right? So emphasizing small. Can you approximate computing for small devices? That's one. In an energy-aware manner, right? And think of a heterogeneous fabric. You might have some small, some bigger, some larger. So can you quickly see if you can leverage the computational resources of different types of devices? And the second is One Health. So can you do computational genomics in a way that the results are interpretable? So that is a big thing of our second thrust. This is the impact of the two of them. And then a unifying goal, I'll let you read that. So those are my destinations. And then there's a little bit of a port left in me. It comes on and off. So that's my little poetic latitude in this talk. I'm going to read that because I really love it after I wrote it. I actually wrote it this morning. Deadlines propel us forward. Detours leave us with the calluses of transformation. And destinations remind us that every step was worth it. For in the end, the journey itself and the people, both present and cherished, who made it worth our while, are the true treasures. That's actually a picture from my summer travels. And that's actually me at the peak. I went to the Bay Area to visit a bunch of companies this summer, and there they actually go mountaineering. All the techies go mountaineering every Saturday morning. So I had my conference at 8, and I went mountaineering. Mountaineering sounds cool. At 5 a.m., and I was at the peak. I think that's just around sunrise. So yeah, and I also, for those of you who always like doing something and if you're standing in line to vote, do Duolingo. So I kind of know French, broken French. So the life of a professor, deadlines, detours, and destinations. And I love it so far. And sorry, this is crammed up. I couldn't leave out a picture, so if you don't see yourself there, it's maybe because I didn't have a picture. I spent like a lot of time trying to put all pictures and filling every hole and nook and cranny. But these are the awesome souvenirs. That's actually my grandmom. She's cherished. And Bernie is right next to that. I can find a story behind every picture. This is amazing. This is from my NAE, Mike Lodish. He nominated me for the Frontiers Symposium. Carrie's there. She's been amazing in helping me develop a lot of these machine learning modules in biotechnology. I think, if I think of wine, I think of you, but I think I have a wine picture somewhere. You have to look for it. But I see Shupriya is there. I think right now I don't have quantum, and quantum is not going to be there, which is awesome. I'm looking to aggregate things and consolidate things. So yeah, I think College of Engineering and College of Ag, it's amazing to be in both colleges. I get the best of both worlds, I'm tempted to say. This is from the College of Engineering office hours. And I actually have a demo. I don't think I have time for it, but maybe after questions, I'll just play it. So I also learned how to do demos, and I really like that demo to show how our work really beats the baselines. So with that, that's the end of my talk.
Thank you so much, Shamali. So as you can imagine, students in our classroom leave quite energized by Shamali's presentation style. So we have time for questions from the audience. So if you've got a question, raise your hand and I'll bring you the microphone.
When was the first time you knew you wanted to become a professor? And since then, when you knew until now, have you been joining all these dots, or did it all come in the flow?
Yeah, this is funny because ever since I was a kid, I always liked studying. Like I liked the idea of having a career where I just study. I learn more. I'm fond of academics. So I kind of knew I wanted to be in academia, something where I just study. And then, believe it or not, from College of Engineering, I got a future faculty fellowship. So it was always there. But of course, at points, I tell my students, because I feel like if you want to be in industry versus in academia, the path might be slightly different. And as you're like graduating, it'll be nice, for example, and I'm learning this myself, that you start writing some proposals, right? Because sometimes, luckily in my PhD and in my postdoc, I got a lot of latitude. Some people like it, some people don't. So I got a lot of freedom. And I was able to come up with, this is what I want to do next. So that's kind of sometimes a little bit intimidating. If it's not intimidating, then maybe you're a natural. So it's a little bit of both having that knack and then also cultivating it. Because sometimes you might not know that knack is there somewhere buried within. So yeah, attend a lot of talks. Attending a lot of talks is very important. I feel like that opens up ideas. And maybe the other thing I tell my students, read a lot of the NSF solicitations, see who are getting the funding, like what kinds of projects are getting funded. So if you go to NSF, their project search, see what kinds of projects are getting funded. So I feel like that is a great way. I actually need to do that again. But sometimes it's, also exploration and exploitation. So you sometimes have to decide how much you want to do and how much you want to drill down. So that's another thing. So not exactly answering your question, but when you're a graduate student, it's nice to explore some so that you can kind of find these areas that resonate well, because that's going to form your early days of your career.
All right. Good afternoon, and thanks for the presentation. We really appreciate it. I want to be on both sides of the divide. I want to be in academia at the same time industry. So what are my options? Thank you.
Yeah, that is a very easy question. Have a startup and have a university where they don't make it that hard to do a startup. I'm still learning the ropes, but I think we have a kind of an infrastructure that tells you how to seed the startup. Honestly, the first grant that I got from OTC, I got 2 Trask Awards that really helped. But the first grant that you get, they tell you have to have an LLC. So the grant has to go to your LLC. And then you realize, it's really easy to start a startup. Just start a startup is really easy, right? But then to get the funding and all of that, but it's a chicken and egg problem. Unless you have the startup, you don't do the next few things, right? Because like I said, the life of a professor is a lot of deadlines, right? And if the startup is not kind of giving you those deadlines, sometimes your deadlines take precedence, right? So if you want to do both, it's hard. It's very hard, but you have to maybe create, and this is telling myself as well, create artificial deadlines for your startup, right? Like, because the real deadlines come when, in CS, we have a lot of these conferences. I submitted 2 Eurosys papers last year, and there were deadlines. And these deadlines are anywhere or not. So a lot of my students know they're 8 a.m. or 7 a.m. in the morning. But create some deadlines that you don't just think of quasi-deadlines or pseudo deadlines so that you can also do the startup. It's sort of my answer to that question.
Hi, is this working? It should be on. Okay. So I'm actually a undergraduate freshman here and in engineering, and I still don't have an idea of what I want to do. Like, I kind of came here because I wanted to engineering, but also because, so the main question I have for myself is whether I want to go into the industry or more into academia. Because
I can take this question from there if you want.
Yeah. How do I know if I'm more suited for industry or academia?
Yeah. So 1, read my paper once it comes out, Science Perspective. I will tell you the way to do that. And no, I feel like I really want that paper to be helpful, like how to do both, right? And I feel like sometimes the boundaries are not that hard, right? Like sometimes there are, if you're the person doing it, right? Like I've had these new, I have funding from Microsoft Research, I've had funding from Adobe Research, I've had an Amazon Research Award. So a lot of the times, industry wants to work with academics, right? And I feel like while writing this paper, some of the things that I saw from the different industry people and the academics who've been writing and the startup founders is that there are some things that industry does really well. So industry might do stuff well that is like right there, like the current problem, right? Whereas academics might be able to do stuff that is going to be a problem 10 years down the road, right? So by working together, you keep that exploration alive. So in some ways, industry exploits and academia explores, right? And in life, oftentimes, this is my favorite algorithm. This happens everywhere. It's hard to beat this. So I feel like at this point, your first year in undergrad, keep an open mind, do lots of internships, because when you're in university, you can work in teachers' labs, professors' labs. Oh, and by the way, I've had freshmen in my lab. I've had at least 2 freshmen in my lab, and I have had 3 high schoolers. During COVID, I had 2 high schoolers who work remotely, and I love it that the first high schooler who graduated from my lab is a UIUC CS undergrad, and he came visited us about a semester ago, and he actually wants to work with us again. I told him, and the funny thing is, he's from the Bay Area. He told me, my brother, who's in 9th grade, can he also join meetings? So the first meeting, both of them joined. I'm like, wow, okay. I feel like a little bit too early to decide. So at this point, keep your options open, right? And just soak up everything. I'm actually a little bit jealous of you because if I knew what I wanted to do now and I go back, maybe I would have done exactly the right things. Less number of detours, but do you like it? Like it's going to be like just exactly the stereotypical journey. I actually like detours. So let it unfold a little bit, but I would say maybe summers, take advantage of internships, and during the semester, check out some labs. If you like a lab, stick around. One of the things I notice that undergrads, sometimes they're really sharp, but once they face a few rejections, some really sharp ones, they'll be like, oh my gosh, this is not my cup of tea. So I think it's also nice to maybe stick around a lab for a little bit longer. Don't just be flighty, move from lab A to lab B. Stick at it. Sometimes persistence and hard work beats the smarts. So remember that. Yeah. Be relentless. I like that. That's actually a favorite thing of mine. Be relentless. Don't give up.
Molly, thanks for the presentation. You've worked with some really, really interesting people in both academia and industry from all over the world. How did you make those connections? So what's the secret to finding some of these phenomenal connections you've had?
Yeah. So use your infrastructure. I remember, Bernie, early on when you became dean, you had this thing that you can write a vision paper, and you had like $10,000 for it, for what it's worth. I think use the kinds of benefits your institution gives, so grab them. Sometimes you might think, hey, vision paper, 10,000, it's not a lot of money in a academics portfolio, but actually getting that paper out of it, I reached out to people from Microsoft Research. I forget, at least a couple different industry folks. I think that was actually my first couple years, that vision paper. And I think that vision paper, sometimes industry likes it, that there is a tangible product that comes out of it. So we're actually writing 2 more. We are writing one to PNAS Nexus, a slightly more technical one that came out of the CPS PI meeting. We're almost like, I really have to shove it out of the door. Like, it doesn't have a deadline. I have to come up with the deadline. The second one, I'm writing the science article, right? And sometimes, remember this other thing. Sometimes these people are really busy. So sometimes you have to be good at, this works really well. Like, set up a meeting, like half an hour. And this actually, I learned from the NSF PI meeting organization committee. Closer to the workshop, they used to have a meeting, I forget, every week or every other week. Like, I think the frequency increased. It's just half an hour, exactly half an hour. But that makes you accountable. Hey, what have you written, right? And moderate that meeting. Every person gets a chance to present and point out, have something to present and point out what is it you've written. So for this paper, for example, I have a professor from Stanford, and he told me he has some amazing experiences. And then, sometimes what helps is just get on a call. And because sometimes if your emails, they're busy, everyone is busy. I do that a lot. So just get on a call. And I got on a call, and we chatted for half an hour. I typed it down, got some amazing insights, right? And this guy, he's also a visiting professor in Google, right? So I actually got Stanford and Google out of the same guy. He actually knows you, Shubhashish Mitra. He was talking about you. So we have parts from his thing and I kind of added him on later. So sometimes use these opportunities, leverage them to get more people on. And also a lot of these panels in these workshops, right? We're having a new workshop here in Purdue in December, inviting speakers. A lot of them really want to do stuff outside of their regular, sort of more mundane industry stuff. Like, they want to go out there, but maybe they need like a channel. So if you give them a very tangible channel, it might be a win-win. So I think that has helped a lot. And also, I have this conference, almost attended this 2-3 times, and now I'm the program chair. It's in Bangalore. There are lots of people, tech people, who go to the Silicon Valley of India there, and I think I've made lots of connections there. So conferences have helped a lot.
Other question? Right, Shamali, you may have a minute if you want to do your demonstration really quick, I think.
I never let an opportunity go. Okay, so here is a demo of a Proxstat, and you see that for the specific computer vision task we are doing object detection. So Proxstat, we measure the accuracy and latency, and you see that when there are no competing applications, so no contention, Proxtet does about as well as Proxtet, and you see that for the specific computer vision task we are doing object detection. So Proxtet, we measure the accuracy and latency, and you see that when there are no competing applications, so no contention, Proxtet does about as well as FRCNN plus MF. FRCNN is the leading edge object detection algorithm, and median flow is the leading tracker. So we see Proxtet is slightly better than FRCNN plus median flow in the absence of contention. Now, if you consider a case where you have resource contention on an embedded device, so this could be a mobile phone or it could be Jetson. Now, resource isolation on these embedded devices is inferior as opposed to server class machines. So you see that a Proxtet has an accuracy of 94% again, and in terms of latency, the latency shoots up initially, but because of the aggressive approximation by a Proxtet, the latency quickly recovers. In this case, latency, the lower, the better. However, you see in the case of FRCNN plus median flow, the accuracy is again about the same, but the latency stays high because it is not able to approximate. So essentially what a Proxtet is doing is for each frame, it is picking the minimum depth. So it is doing an aggressive approximation by picking the right approximation. Yeah, just the takeaway is we do aggressive right-sized approximation so that FRCNN plus median flow is our competitor. You always have to have a baseline, and we show that we are able to right-size computation, and by doing the right kind of approximation, we are able to give you the latency guarantee. So this is a census, slightly dated paper 2020, but the reason I put this on is because now we are hardening this for the Army. They're very interested in this, and then we are coming up with additional optimizations on top of this framework that is still an active area of work. And this is for 2D object detection. So now we are also doing right-sized approximation for 3D object detection. So this is an ongoing line of work. And the part that we finish, now we are hardening the code. Joe is in the room. And Sheetal is in the room. They're very nicely hardening the code. We've given it to the Army, and they really like the code. So it's a combination of engineering and innovation.
All right, let's thank Shamali again for her talk. And thank you all for joining us for lunch today. And there will be several more of these over the course of this academic year. So look for more of these kind of talks from recently promoted associate professors. Thank you.